Good evening, all. Welcome to week 3 of live sessions for the Fundamentals of Convective Heat Transfer course. This is the third week in the session. In the last week, we covered topics related to the boundary layer derivation, but we haven't actually solved the governing equations. In this particular session, we will actually solve, we don't solve the equation, but then we present something called a Blasius solution, which kind of reduces the equations to the partial differential equations that we derived in the previous class into an ordinary differential equation. And once you're familiar, if you're familiar with any of the how to solve ordinary differential equations, then you'll be able to solve those equations. But in the session, we will only present you with the solution of those particular equations. Like we don't tell you how to solve it, but then we will give you the solution directly. First one is the Blasius solution, followed by the Pohlhausen solution, in which the first one is about the hydrodynamic boundary layer. And the second one is the thermal boundary layer. Once we derive this, both of these are for flat plate. When we have a flat plate, both these are for flat plate. Where you have something like this, which we discussed in the last week. We have U infinity, T infinity, and then we have delta and delta T. Where this the relative magnitude of delta by delta T will be a function of Prandtl number, which we discussed in the last week. It will be 1 by Prandtl, delta T by delta is proportional to 1 by Prandtl to the power half. So followed by these two flat plates, then we will discuss something called flow over a wedge, where you have a flow like this, where the walls will be like, say you have a sharp corner like this, and then uniform flow comes like this infinity, and what happens to the flow here and here as it goes, how it develops, and the governing equations. We'll solve the governing equations using the something called a similarity technique. That is the same technique that will be introduced even in the Blasius solution. Once we get the that for this particular problem, we call it a Falkner-Skan solutions. After this, we will come up with two important definitions, which we will use in next week as well. So that's called the displacement thickness and momentum thickness. We'll just briefly define what these quantities are, but we'll take up more problems on it in upcoming weeks. Followed by all these derivations, we will solve some problems, some numerical problems, so that those of you who have not gone through the lecture videos, I would like to give a summary of all these derivations first, and then we will go to problems solving. So last week we stopped at something like this, where you have the energy equation given to you in this particular way. But then before trying to solve these equations, we kind of non-dimensionalized it. So we have some non-dimensional parameters defined like this. So why are we doing this non-dimensionalization? Is so that your problems like you will be able to apply it for wide class of problems using the non-dimensional parameters instead of the actual values. So velocity, we will define the free stream velocity as our scale. So the non-dimensional velocity is given by the actual velocity with respect to the free stream velocity divided by, and theta is defined in a way as p minus t infinity by tw minus t infinity. So at the wall this will be 1, and as you go away from the wall this will go to 0. Xa star is xa by L, and p star is with respect to the dynamic velocity, dynamic pressure, rho infinity square, and p star as the time scale divided by time divided by some time scale. The time scale is obtained by dividing the length scale by velocity scale. So this is meter per second, that will give you seconds. So that will be the relative corresponding time scale. So if you substitute these equations back into the original governing equation, you will get this non-dimensional equation, where if I group the terms together, this is my k by rho Cp is my alpha, that is the thermal diffusivity. So I multiply divided with by nu. So it will be alpha by nu is 1 by Prandtl number, and nu by u infinity L is my Reynolds number. This is one quantity, and then this particular quantity is what we are calling is Eckert number, and the quantity here is the Eckert number by Reynolds number. As we discussed even in the last class, these two terms are usually negligible in most of our cases, and we'll be only dealing with this first term. Yes, that is because we have very low speed flows. So these are the final equations. And the non-dimensional number, Eckert number, is basically the ratio of the kinetic energy, U infinity square, to the enthalpy difference across the boundary layer. So this is some kind of, if you relate it with respect to Mach number, you can see this as the speed of the flow is very less, in which case the Mach number is very less, less than 0.1 or so. Then this particular term itself will be 0.01, and this term can be neglected from the governing equation. Compared to the other terms, this term will be very small, these two terms, because the Eckert number is very less. When as the speed increases, as your Mach number increases, this number becomes more and more significant. And in our case, we are assuming we have a laminar incompressible Newtonian fluid flow with constant properties. So when you say incompressible, it means the Mach number is low. So this is low, so you can neglect that term. And this is the governing equation that we will be using from here forth, henceforth. Now let us start with the Blasius solution. So in the Blasius solution, we'll start right from the equations that we already derived. So we have the governing equation, one continuity equation, and the momentum equation. The momentum equation will be only one of the equations along x direction. Along y direction, we have neglected the momentum equation, because if you recollect, in the last week we identified that the scale of the vertical velocity is of the order delta by L times horizontal velocity. So if you recollect, will be as order u infinity into delta by L, where delta by L is a very small quantity, so we actually neglected the y momentum equation. The y momentum equation will be of order u infinity square. You can go back to the derivation there. But the main observation that was done by Prandtl long back was something like this. So if you observe the velocity profiles at different positions, say at position x1 and position x2, these profiles are kind of similar to each other. Like the magnitudes may be different. The value here is 0. Eventually here it is u infinity. But if you draw a straight line here, something like this, the velocity here at this point and velocity here at this point are not equal to each other. But if you were to go along a different line, so why should I go along a horizontal line? So if I choose a new coordinate system, new variables in such a way that the velocities will be same. That was the idea they were trying to do. And when they observed that if I transform my coordinates in such a way that if I choose my axis as y by delta of x, where this delta is again a function of x, delta will keep changing with respect to x, and then plot u by u infinity, all these profiles are actually falling into a single one. This is a main observation, and this is what we are calling the similarity, self-similar solutions. This keeps coming up in several other places as well. So the idea here is beyond a certain point. So like in the initial region, very close to the leading edge, this might not be true. But as you go far and far away, what happens is the solution here, like if you know the solution at this particular point, if I know the solution at point x1, and if I know point x2, then I'll be able to reconstruct the solution without having to know anything about what is happening here. All I need to know is this profile. So at any point, if I know the velocity profile, I can calculate the velocity profile at any other point downstream of it. This is very similar to the idea like your similar triangles. If you might have done it in your +2, where you have two triangles. So you have a triangle like this, another bigger triangle like this. If you know if I already know that these two triangles are similar to each other, so this is 1, and one of the dimension is 1 is square root 2. And if I say that this is 2, then you will be able to calculate all other dimensions. When I say that both of these are similar, the ratios have to be proportional. So you'll be able to calculate everything else. So you know if this is 2, this is 2, and this is 2 root 2. This is the whole idea in the similarity. The same logic will be extending here. So now we define a new function eta as some y times g of x, where g is basically 1 by delta, in such a way that this u by u infinity is now not a function of x comma y. Instead, now it becomes only a function of single variable. And that single variable is this particular eta that we are defining here. This is the similarity variable. So that our u by u infinity is a function like this. Now all we need to know is this function g of x, which we do not know as of now. So this is again, if we start with the assumption that eta is of this particular form, so and substitute it back, we can see what happens to the governing equations. So what we are trying to do again, as I said, our aim is to convert the governing equations in terms of eta and f. So my original equation, I have u v, like I need to find u and v as a function of x comma y. But now I'm saying, okay, I don't want to solve this in terms of two variables. I observed that there is some similarity here. So I want to reduce it to a single variable problem. So I define my new variable as eta, which is y into y times g of x. And I want to write my function in terms of this. So we start from that particular term. So we define eta as y times g of x. And we already define some function f, which we do not know as of now what this function f is, but we define that it is self-similar. So u by u infinity should be f of eta. So what we want to do is to get the governing equations in terms of f. So which means I have to find these governing equations in terms of eta, and then that will give me a final governing equation. So that is what we'll be doing from now. So these are all mathematical manipulations. So it's not you can do it once with your hand to get familiarized with this. The idea goes in the right way. So in order to obtain del u del x, you apply the chain rule. So this will be del u del eta into del eta by del x. So del u del eta will be u infinity times f prime, and del eta del x is something that you can calculate from this. It is y times g prime. Similarly, you can calculate del u del y, which is del u del eta times del eta del y, and similarly del square u by del y square. Once you get these terms, you can substitute them back in the momentum equation. In this, we know u, we know del u del x, we know del u del y, we know del square u del y square. We do not know the value of v. So once you substitute all those terms, you will calculate the value of v from them. So this is the expression for v. Now I have two governing equations. In this, all I have used is the momentum equation. I have not used the continuity equation. So this v cannot be like this. Like in order to get my equation, like what I have to do is substitute this v back into my continuity equation, so that I will be able to relate, like I'll get one equation in terms of f and g prime. So from continuity, we already have del v del y is minus del u del x. We already know what is del u del x. We substitute that back here. We know v. So if you calculate del v del y, which is del v del eta times del eta del y. Del eta del y is something that we calculated before. We can substitute that back. If you rearrange the terms, so this is the equation we will be getting. The important thing here is we are rearranging it in such a way that these terms are all functions of eta, and these terms are all functions of x. So these two are, I'm saying that there is something which is function of only eta, and then there is something else which is only function of x, and both are equal. That can happen only if both are some constant. So it should be something like this is some eta, this is some eta, this is some eta, and all of them are cancelling each other, and this is becoming some constant. And similarly here, g cube is some function of x, g prime is some function of x, but when I divide them, that particular quantity should not be a function of x. Only then these two terms will be equal to each other. So with that logic, we will start solving each one of them. So let's take one half of it. So if you take the second one, where u infinity by nu g prime by g cube prime equals to some constant k, this is an ordinary differential equation which we can directly solve. In order to get this constant, we need to know the boundary conditions. These are where the physics comes in. Hi, good evening. Yeah, so I'm just quickly going through the derivation once again. If you have already gone through the lecture video, if you have any doubts, you can stop me in between. If you have not, then you can just go along. Yeah. So the idea is now to understand what is the boundary conditions for this particular g function. The way we define g is eta is y times g of x. So the only boundary condition we have is near the leading edge. So like if you get back to the original problem, the boundary conditions we have are near the wall and near the free stream. And so at x equal to 0, near the leading edge we have one boundary condition, at y equal to 0 we have one boundary condition, and as y tends to infinity we have other boundary conditions. With these conditions, we'll define what g of x is now. Now we are saying that near the leading edge, the boundary layer has not started developing. So there delta has to be 0, which means this particular function has to be 0. Delta, if you recollect, so we have defined eta as y by delta, and that is y by g. So I'm saying delta tends to 0, which means this particular quantity has to go to 1 by g has to go to 0. So this particular c1 will be 0. So from there I will get the expression for g. Now again, this is an arbitrary choice we are making. Once we solve the governing equations later, once we get like we have arbitrarily chosen k equal to -1 by 2 because we do not know yet what this value has to be. So this is an arbitrary choice at this point. but we are only trying to derive the governing equations. Once we solve the governing equations, we'll actually get what this particular value k can actually be, like after solving the equations. That we will see little later. But now once we have this g of x, so we can calculate eta as y times g of x. So this is my similarity variable. So the actual similarity variable will be some function of this, because I have chosen k to be minus 1 by 2, but it could be anything else. So it will be something that is proportional to this, and that proportional constant is something that we do not know at this point. But without any loss of generality, we can choose this value, because all of this this is actually going into a differential equation, so all the constants will get cancelled each other. Now we'll take the other half of the equation, where we have 1 by the function that is the term which is only function of eta, so which is this term. Like we have two terms, one which is function of x and the other which is only function of eta. So we can solve, again this is a normal equation which we can solve. But in order to solve this, we have like if you integrate this, we have integral f times theta, and this is something we are denoting with a new function little f. And this little f, again I can take the derivative, that will be equal to capital F. Now I can write these terms, f double prime will be f triple prime, like little f triple prime, and capital F prime is little f double prime. If I substitute them back, so this is the governing equation I'm getting. This is what we are calling base case equation. Now, if you remember, we started out with a partial differential equation, and we eventually ended up with an ordinary differential equation. Now, in order to solve this equation, now we need to get the boundary conditions. So in order to get the boundary conditions, we need to know what this f represents actually. So unless we know what the f is, we do not know how, we cannot actually keep any physical boundary conditions. So to understand f prime, so if you recollect, my capital F is related with f prime, and I have defined u as u infinity times capital F. So my f prime is u by u infinity. So this particular quantity is like the derivative of some quantity is proportional to u. So this is something very similar to the stream function, the way we define stream function. So if f is something that is proportional to stream function, if we define u as del psi by del y, which is basically del psi del eta times del eta del y, and we already know what is the del eta del y, like eta is y times g of x, so del eta del y is g times d psi by d eta. So this is exactly similar to this function, like if you remove the constant here. So this f is something like a stream function. So if you recollect what a stream function is, the stream function across the solid boundary, like if I write this is my solid boundary, and the stream functions will be something that are across the solid boundary. I can choose any arbitrary value for my stream function, because the stream function is a scale with some constant. I can always when I take the derivative, the constant will just go off. So I can arbitrarily choose what is the value of psi on the surface of this wall, and here we are choosing that to be 0. So if I choose that to be 0, my f of eta is at eta equal to 0, where eta equal to 0 means y equal to 0 is basically 0. So this is one boundary condition I get in this way, and the remaining boundary conditions we'll have at the other wall. So at the wall, we have now that the velocity has to be 0, u has to be 0, and we already know u is proportional to f prime, like u equals to f prime times u infinity. So f prime of 0 should be 0. So this is basically u equal to 0 condition. The other one is it has to be wall, so psi has to be 0 on the wall. This is another condition. And we know that at the far stream, the velocity has to be u equal to u infinite. So which means f prime as eta tends to infinite should be 1. We can also write in terms of f double prime, but this is a third order differential equation, so you just need 3 conditions to be able to solve it, and we have 3 conditions here. With this, you should be able to solve. But how do we solve these equations? We have not discussed how to solve these equations in this particular lecture, but if you're interested, for those of you who are already familiar with something called state space method, you can convert this into a set of 3 ODEs. So this is basically a third order ODE. So you can define new functions and then convert it into 3 ODEs and then solve the 3 ODEs simultaneously using any other method that you like, say maybe Rangakuta, or you can use Euler method or any other method of your choice. If you're familiar with MATLAB, then there are default functions to do this for you. All you have to do is just write it in the state space form with this particular boundary conditions and then solve it. The only problem is all these methods are time marching, in the sense they start from eta equal to 0 and then go towards eta equal to infinite. When in order to do that integration, you'll have the first problem that you need to know is So if I convert this third order equation into state space form, then I'll have three equations. One will be for f prime, the other one will be for f double prime, and the last one will be for f triple prime, which means I need to know f of 0, f prime of 0, and I also need to know f double prime of 0. But at this particular point, at least with this boundary conditions, I do not know what is f double prime of 0. This is an unknown. So unless I know f double prime of 0, I will not be able to solve these equations using any of these methods that are directly available. So that's where you have something called shooting technique. The trick there is you assume some value for f double prime 0. You assume that value and then do the time marching. Get the value of f prime of eta tends to infinite. Again here, when I say eta tends to infinite, it doesn't mean you have to integrate from eta equal to 0 to say 10 power 10 or something. But if you do the calculation yourself, you'll find that after around say 10 or 15, this value will actually f prime will actually go to 0. Sorry, f prime will actually tend to 1. So you don't have to actually integrate till a very large number, but then the number of times that you have to take will be higher. So the question is, you assume a particular value for f double prime of 0 and then solve till eta tends to 1 or something where the f prime will actually goes to 1, and then you stop your integration there. But that particular thing value will not be equal, will not exactly be equal to 1. So this is basically like solving using say secant method. If you're already familiar with secant method or Newton method or any other method, this is basically solving a nonlinear equation. So assume a value, you try to see whether it is matching to 1 or not. If it is not matching, you change this assumption. So you keep changing this assumption and then till you get f prime to be equal to 1. How to change that thing is where you have different techniques, Newton or secant method, where you use the gradient information to decide how to change this initial assumption that you have taken. We're not going into that, but let's say you have already solved and the solution is available to you. The solution says that you have that f double prime of 0 is 0.33206. And in our, as I said, this value, instead of it won't be exactly 1, but if you have taken the value to be close to 0.99, then eta is actually 5. If you go even further, then it will be 0.999 and so on. So with eta equal to 5, we know eta is delta times square root of infinity by nu x, and we are saying that equal to 5. So my delta by x is 5 square root of rex. So this is the scaling, that this is a relation that will be useful in many other places later. So if you want to determine what is the boundary layer thickness, that is approximately given by this particular relation. If you know the Reynolds number at that particular x from the leading edge, then you can calculate what is the order of delta with respect to x using this relation. And the most important thing from like why do we do all of this is to estimate what is the net drag force that we need to exert, the net drag force exerted on the surface. So to do that, we need to calculate the shear stress, which is given by mu times del u del y at y equal to 0. So again, using the non-dimensional like u by u infinity is f prime, you substitute that back. So this is the equation we have. Again, you can use the chain rule, df d eta times d eta del eta del y at y equal to 0 and eta equal to 0. You can substitute them back, and the equation I will be getting is something like this. Now, again, to put it in terms of non-dimensional terms, we have the local screen friction coefficients, CFX. CF as a function of x is tau w by half rho infinity square. This is my dynamic pressure. So if you substitute the equation back, so this is the equation I'm getting. So the local screen friction coefficient is 0.664 times square root of Rex. So as you can see, like near the leading edge where your Reynolds number is very less, the screen friction will be very high. But as you go farther and farther from the leading edge, the value of this Rex will keep on increasing and the local screen friction will keep on reducing. So the shear stress will be much higher during the near the leading edge compared to the farther edge. And you can also get the same intuition. So if you see the profile, if you recollect the profiles that we have before, so have something like this. And then as you go further and further, this expands to much wider region. Which means if I have a particular velocity here, the same velocity would be obtained a little higher here, which means the gradient of that particular velocity, del u del y, is actually reducing as you go further and further. So as the gradient reduces, your shear stress will also reduce. If this value reduces, your shear stress will also reduce. That is the same thing that is getting reflected here. All we have to know, all we now know is in a more we quantified it in more precise way. that it varies as square root of x. And the other thing that you have to notice here is this relation that if your kinematic viscosity is increasing, then the amount of the resistance to the particular flow from the hot surface is also increasing, but is proportional to square root of mu. And as your velocity increases, Cfx will actually reduce. These are all the things that we know intuitively as well. So if the viscosity increases, we know that the shear stress will increase. That is the same thing that is getting reflected in the equation. This is with respect to the Blasius solution. Now all of this is for the hydrodynamic boundary layer. The next one is for okay. So before going to the thermal boundary layer, the other most important thing is what is the net force acting on the surface. So we know the shear stress, so all we have to do is integrate the shear stress along that particular surface. So if we just substitute that back and integrate, this is the equation we are getting. So you can see the same thing here. As the length of the plate increases, the total amount of force will keep on increasing because the amount of surface is increased, and this is directly proportional to the kinematic viscosity. Now the average skin friction coefficient is F by half rho infinity square. This is again the same term. So this is basically 2 times whatever we have out there. Now comes the thermal boundary layer. Here also we use the same idea as before. We need to get we use the similarity method, where in the previous case we have u going from 0 to 1. So basically we define a new non-dimensional u, where u star is u by u infinity. So u by u infinity will be 0 here, and it will go to 1. In a similar way, we define a variable theta as p minus tw by t infinity minus tw. At the wall, this will be 0, just like how u by u infinity is 0. And as you go towards the free stream, this particular quantity will go towards 1. So if Prandtl number is 1, which is basically alpha equals to mu, then theta and u are basically the same. It's like in the governing equation, if I just replace u star with theta, then they are basically the same. So the thermal and the hydrodynamic boundary layers are the same when Prandtl number is 1. Again, the most important assumption that we are having here is even in the previous equation that we have seen is in the previous equation that mu is assumed to be constant, is not a function of temperature. So all these derivations are assuming that the properties are constant and they are not changing with temperature. Only in that particular case you can solve the momentum equation and continuity equation. You can solve continuity and momentum equation together without having to depend on solving the energy equation. So these two equations are completely decoupled from each other in that way. So first, once I solve the continuity and momentum, get my velocity, and use that velocity here, solve for temperature. That is possible because the properties are not functions of temperature. This is something that you need to keep in mind. So maybe I'll just write now. Okay, with that in mind, now let's say if Prandtl number is not equal to 1, so how do you go about solving that? If we use the same technique as before, we use the same similarity variable, theta as y times square root of u infinity by mu x. And then, but now we have to get these terms as well, del t del x, del t del y. Again, we use the chain rule, del t del x is del t by del eta times del eta by del x. And del t del y is del t by del eta by del y. And these terms we already calculated before, so you can directly substitute them. But here we are not assuming this tw to be constant. We are saying that tw could actually be a function of x. So you have dw by dx. So let's say tw is not constant, but could be a function of x. In that case, if you substitute the equation, so del t del x is this particular term, and similarly you can calculate del t del y. Once I have these two, I can calculate del square t del y square and substitute all this in my original equation. I use the solution that I obtained from the Blasius. So u is given by u infinity times f prime and v is given by this particular term. So if I substitute them all together and rearrange the equations, this is a little bit of rearrangement. So the terms get cancelled each other. This and this term will get cancelled each other. and I'll be left with the following governing equation, something like this, where if I again group terms together in such a way that all the terms that are only function of eta and all the terms that are only function of x, that is what I want to separate and then make them equal to some constant. So these terms will be only function of x and these terms will only be function of eta. And this can happen only if each of the term is actually a constant. So if let's take the first term, this is only function of x. So from this I can calculate tw to be. So if you just integrate this, this is ln of something and then this will go into the power. So tw is t infinity plus t into x to the power lambda. So if lambda equal to 0, then tw is constant. T infinity plus some constant. The constant can be positive or negative, whatever it is, but it's basically uniform constant, uniform wall temperature. And the other half is where you have the terms that are only function of eta equals to some lambda. So if you rearrange the terms, this is the equation I'm getting. Again, for a constant wall, this lambda is 0. So this will be the governing equation that I need to solve for. So how do I solve this equation? This is also a straightforward one. You can also solve, like you have to just integrate this, you'll have e power some term and you'll be able to solve it. But then I already know, in order to solve this equation, I need to already have the solution for f. So first I'll solve the Blasius equation. I'll use that particular f, substitute that here and get the value of theta. But this solution theta is now a function of two variables. So previously f is only function of eta, nothing else. But now we have this equation, the solution of this equation will also depend on the value of Prandtl number. So now theta is a function of eta as well as my Prandtl number. So assume a value of Prandtl number, like given say Prandtl number of 0.117, whatever value you have, substitute that here and then you solve this equation. So the boundary conditions are at the wall you have theta to be 0 because t equal to tw, and as it goes to infinity, theta will go to infinity. This is just like how your u by infinity goes. Near the wall u by infinity is 0, and as you go far away from the wall, u by u infinity tends to 1. So you can solve this equation again using the same techniques, using say Runge-Kutta or another method that you already know familiar with. Like convert this equation into state space form and then solve using any numerical technique. The most important terms that we would get from this solution are the heat transfer. What is the net heat transfer from the plate? That is the question we are trying to answer. In case of hydrodynamic boundary layer, the question we are answering is what is the net frictional force that I have to overcome? What is the net resistance offered by the horizontal flat surface onto the fluid flow? That is the question we are answering there. And in case of the Pohlhausen solution, we are trying to answer what is the net heat transfer. So that is minus k times del t del y at y equal to 0. So you can substitute the terms back. So and use the chain rule. So del t del y is t infinity minus tw by del t del y, and this is del theta d theta d eta times del eta by del y, and this is basically theta prime of 0 and del eta del y. We already have the equation. Now if I use the definition of heat transfer coefficient as q by delta t, so this minus will just go off with these two terms. So I'll have k times theta prime of 0 times square root of unit x. So if you rearrange this again, the Nusselt in terms of local Nusselt number, which is hx by k, the x will go into x square, so it will become u infinity x by nu. So this is my local Reynolds number. So theta prime 0 times the local Reynolds number, where again this theta prime 0, as I said before, theta is a function of both eta and the Prandtl number. So theta prime of 0 will also be a function of Prandtl number. So you have to solve the equation for different Prandtl numbers, get the different values of theta prime of 0, and then identify and then fit a curve for those values. If you do an average value over the length of the plate, then you will have NUL as 2 times the value of this into REL to the power half. What is the value of theta prime of 0? So what people have done is solve the equation for different values of Prandtl number, and they develop these power law correlations for that particular data, and the theta prime is given by these expressions. So if you substitute them back, the Nusselt number is given by you can take the average Nusselt number is given by 0.664 times Prandtl to the power 1 by 3 times Reynolds to the power half in this particular range, which is the one that will mostly see with air or water. Are there any questions up until here? I hope everything is clear. Now, if you define a new number, like say a Stanton number, as something as Nusselt number divided by Prandtl times Reynolds number, and if you observe the value that you get over here, that this particular quantity, the Stanton number times the Prandtl number per half, is Tfx by 2. So this is something that is relating the heat transfer, and this is something that is relating the fluid friction. So what Reynolds for Prandtl number equal to 1, we have the Stanton number given by Cfx by 2. This is basically called the Reynolds analogy, or the Colburn analogy, is where you have the Stanton, the Nusselt number and the local skin friction coefficient are related to each other in a given particular way. And it was observed that this particular relation is, you can use this relation even in some scenarios where you do not have this flat plate, like it can be applied in other scenarios also. So, but what is the use of this analogy? The idea behind this is, if you see the governing equations for Prandtl number equal to 1, the if you recollect, for Prandtl number equal to 1, the governing equations like u and theta are equivalent to each other. So which means the gradient should also be in some way related with each other. So that means this Nusselt number and local skin friction should be in some way related to each other, and that relation is what is given by the Stanton number. So if you know one of these terms, you will be able to calculate the other term. Now coming to the next case, where you have the, as we refer, the other half of the term, where we have Tw minus T infinity Cx to the power lambda. For a constant wall, lambda equal to 0, so this is some constant. But let's say we have a variable wall temperature. Then what would be the case is, let's say you have a uniform heat flux condition. So when there is uniform heat that is getting added to the fluid as the fluid goes along, then its temperature cannot be constant. The temperature keeps increasing. So how would the temperature vary? So we will take the expression that we obtained before for Q double prime, and we are saying this particular term has to be constant. Constant in the sense it should not be a function of x. So you know Tw minus T infinity Cx to the power lambda, and we have x per half here, so this will be lambda minus half. And I want this term not to be a function of x, which means this exponent has to be 0. So lambda has to be half. So Tw minus T infinity should be c times square root of x. So the temperature will keep on increasing because heat is continuously getting added to the fluid. Are there any questions here? No questions, I guess. And the last part is something called the Falkner-Skan equations, where we have, instead of a parallel plate, we have a wedge here. The difference from the parallel plate is when you have something like here, something like this, the flow will be constant. Like we already seen that there won't be any pressure. The pressure will be constant throughout because the velocity is constant. But when you have a sharp obstruction like this, what happens is the fluid comes like this, and then because of this stagnation, there will be a pressure gradient that is forming here. So you'll have a high pressure region and a low pressure region, and then which means there will be a, whenever there is a pressure gradient, there will be an net external forces which will actually cause a fluid acceleration or deceleration. So the general solution for these kind of cases is u infinity of x is T's x to the power m. Depending on the value of m, you will decide whether that flow is accelerating or decelerating. And how did we get this is something that is beyond the scope of this particular session. You can refer to any of the classic textbooks for this. For the Blasius case, we know that u infinity is constant. So basically my m is 0, beta is 0. So if I apply my Bernoulli's equation, p plus half rho infinity square equal to constant. So I apply take derivative on both sides with respect to x. dp dx is this particular term. So if I substitute the cx to the power m, so I'll be getting something like this. If the flow is accelerating, which means if the flow is accelerating, so the pressure here has to be higher than here. So as you go along the x direction, the pressure should be decreasing. That's when the flow will accelerate. So dp dx should be negative. So if this quantity has to be negative, m has to be positive. So you can solve this equation beta by 2 minus beta positive, which means both of them has the sum or the product of these two terms has to be positive. Then this particular value will be positive. So beta will be in this range. Similarly for the other case. Again, we use the same relations that we obtained before from the Blasius solution, that we already know eta is something like this. Now instead of u infinity being constant, now u infinity is t times x to the power m. So if I substitute the equation back, so I'll have eta as something like this. Again, I'll do the same calculations as before. So I know my stream function, which is g times f, which we already have here. g by u infinity times psi, sorry, u infinity by g times f, which is again the same, from which we'll calculate psi function. And once I have psi, I can directly calculate my velocity. It's like del z del x and del z del y, which will give me my velocity. Del z del y is basically my u component, and del z del x is basically my minus v component. So this is my vertical velocity, and this is my horizontal velocity terms. Now, if I substitute those equations back into the momentum and energy equations, like I got del z del x and del z del y, which are my u and v minus v terms. This is minus v and this is u. I'll substitute them into the governing equations. And again, this is a little bit of rearrangement here. I'm not going into them step by step because they've already been covered in the lecture videos. So if you calculate all these terms individually and then substitute into the governing equation, so the overall terms will be like this. If I group the terms together again, so this is the governing equation I'll be ending up with. So if m equal to 0, which is a case of a flat plate, your Blasius equation will be recovered. So f triple prime plus half into f double prime equal to 0. For a different cases, you can get the same value, like m and beta related with each other. So from beta, you can calculate m equal to beta by 2 minus beta. So for a given value of beta, you can calculate m value and then solve these governing equations, solve these 3 ODs again using Rangakutar, whatever technique you have, solve the equations and get f double prime 0. Like our objective is to identify what is the net drag force and stuff like that. So you'll be able to calculate f double prime 0. Now, in a similar way, you can also solve for the thermal boundary layer, where you have the same idea. Eta will be given as this, just that you substitute u infinity as c times x to the power m, and then you'll get these equations. If I substitute them back, so this is the governing equation I'm getting. So if m equal to 0, you can get back the Pohlhausen equations. Otherwise, this is the general case. Now, the most two important concepts here are the displacement thickness and the momentum thickness. The first one is the displacement thickness. The idea here is when you have a boundary layer that is forming, here the velocity is actually reducing. So the velocity here will be close to the surface, will be close to 0. And as you go higher up, it needs to be increasing. So if I consider a control volume like this, then whatever is coming here, and if you take whatever is going out here, the mass flow rate here and here will not balance each other. The mass flow rate here will obviously be lower than this because the velocity here is reduced. Like as it goes higher and higher, here the velocity will be infinity, and anywhere below it, the velocity is actually reducing. So what happened to that differential thing is, in order to account for the differential, we are giving a fictitious quantity like delta star. So if you consider this much volume, so instead of taking my control volume like this, if I take a control volume like this, then the net inflow will be equal to the net outflow. So what is this delta star? The extra distance I have to go so that by mass flow rate at inlet will match with the exit. So that is this quantity. So where do we use this? Is something that we will see in the next week once we have the integral formulation also. Then it will be much clearer why we need this displacement thickness concept. But put it in another way, if you know the displacement thickness, then you will be able to calculate the mass flow rate directly. So if I know the displacement thickness, all I have to do is multiply this displacement thickness times u infinity times rho, and that will give me the net mass flow rate. Similar idea goes with the momentum thickness. Again, so now we know that the mass flow rate won't be equal on each side unless I add this extra delta star. The question now is, okay, after adding this extra delta star, will the momentum also balance at 1 and 2? So you calculate the net momentum rate going inside at 0.1, and then you calculate the net momentum rate at delta up to from 0 to delta plus delta star, and calculate the difference between these two. So that difference is some finite quantity, and that finite quantity is what we are calling rho infinity square times theta, and this theta is a momentum thickness. So there will be a deficit of momentum. So firstly, we identified that there is a deficit of mass flux, and we decided to add extra delta star so that the mass flux will be balanced. And even after adding the mass flux balance, we observe that doesn't mean that just because mass flux is balanced doesn't mean momentum will be balanced. In order to balance momentum, you might have to go some extra distance theta. It wouldn't be making sense to write it in this way, but then it's a fictitious quantity. So by adding that extra theta, we'll be able to capture the entire momentum also, momentum that is coming inside. And it is observed that if you calculate this, like we already know what is u by u infinity, so this is f prime. and 1 minus u by infinity is again f prime. So you can compute this integral. Once we have the Blasius solution, you can do the integration. Like how do I do the integration? So I can substitute y, write this equation in terms of delta and then solve eta. Basically eta as, you can write y by delta and then make this something like delta times 0 to 1 f prime, u by infinity is f prime. There will be something like this. So I already know f prime that I computed previously from the Blasius solution. I can substitute that, do this integration, say using trapezoidal method or something. So this should not be from 0 to 5 or 0 to 10 up until where that particular value goes off. And then you can calculate this. From this you can calculate theta. Similarly, you can calculate delta star. And if you take the ratio of these two quantities, that is the shape factor, which comes out to be around 2.59 for a laminar boundary layer. And this is again some quantity, like we know that these boundary layers are kind of universal in nature. So if you calculated a value and that, like this is basically like a symptom that you can use. So this is an indicator that you can use. So if in a particular case, you calculated the displacement thickness, like you experimentally measure what are the values of u by infinity, then you can directly compute the integral, get the value of delta star, get the value of theta, and then take the ratio. See if this value is different from this, then it means something is not true in the assumptions that we have taken when we started out deriving the laminar boundary layer equations. Like the Blasius solution, we assume that it has to be some assumption. Say we assumed it has to be laminar, for example. So you experimentally obtain the values of u by infinity, and then you computed the value of shape factor, and let's say the value turned out to be say 1 instead of 2.5. Let's say it is 1 or something. So the value is much lesser than what it was predicted from the laminar boundary layer theory, which means the assumption, one of the assumptions that we have started out is wrong. So this can actually be used as an indicator to say that something is wrong and it's not like the normal boundary layer that you would expect to see in case of from the Blasius solution. So it could be either because the laminar assumption is wrong, maybe some turbulence has started out, or maybe the flow suppression has occurred. Any of these values, flow suppression occur, the values will be higher. If there is a turbulence, it will be lower. So this particular shape factor can actually be used as an indicator to say whether one of these assumptions are correct or wrong. So this is a way to verify whether the laminar boundary layer is existing or not. Okay, are there any questions up until now? We are like halfway through the session. If there are no questions, then we'll solve some problems and then we can end the session for today. I'll pause for a couple of minutes. So if you have any questions, you can raise. You can just go through it and let me know. Okay, I guess there are no questions. Then we'll move on to solving some problems. So the first one is, say, consider you have a laminar boundary layer of an isothermal fluid over an isothermal wall. So if you are given the local friction coefficient, calculate the local Nusselt number. This is something we have discussed just now. So I'll wait for a couple of minutes so you can solve it yourself. Yeah, okay. So where do I start? Start with the Pohlhausen analogy. It says that the Stanton number times Prandtl number Cfx by 2, where this is the relation of deviation, where this Stanton number is given by nu x. I know the value of Cfx and I know the value of Prandtl number. So nu x given by 2 times Rex times Pr to the power 1 by 2. But I do not know the value of Rex, but we know how Cfx and Rex are related. Cfx is 664. Let me just cross check the value. Just so from this I can compute the what's the value of Rex. On 664 by Cfx square. Or you can, if you already know what the correlation for Nusselt number is, you can directly use that as well. So first you calculate the Reynolds number from this and can use the correlation between Nusselt number and Reynolds number. Like you already know Prandtl number, you can substitute that back and get it. Whichever way it is, you can compute the value of Nusselt number. Hope this is clear. Okay, move on to the next problem. So consider a laminar boundary layer formed by flow of 10 degrees Celsius water over 10 degrees Celsius flat wall of length L. Assume the mechanical power Pc spent on dragging the wall through the fluid. If the wall is heated to 90 degrees Celsius, the power spent is pH determined by pH by Pc. So what we are trying to see now is, let's say there is some fluid. Let's say you have a very big container filled with water at 10 degrees Celsius. And then now I have a plate here. That is inside the fluid, or let me just draw a smaller one. So in this container, I have a plate like this. Some plate inside this container, and I am trying to pull this plate. So again, you can just apply. It's like if you change your frame of reference, instead of seeing it from the frame of fluid, if you see it from the frame of like if you're moving with this, the constant velocity, you are pulling this plate with a constant velocity, and then assume you are sitting on the plate. Then according to you, the fluid will be flowing across both the surfaces of the plate, right? So it's basically again the boundary layer. But then the question is, now there are two possibilities. We are saying in one scenario, you have the plate at 10 degrees Celsius. Say in case 1, case C, you're having a 10 degrees Celsius. And in case H, what we are doing is we are somehow heating the plates. They put some electrical wire or something and then heat the plate to say 90 degrees Celsius and then pull the plate. So what do you think the advantage is with that particular way? Like, why do you think I have to heat the plate? Let's say if I'm not heating the plate, I have the normal plate and I'm pulling it. The plate is at 10 degrees Celsius and the surrounding ambient water is also at 10 degrees Celsius and I'm pulling the plate. What is the net power that I'll be using? Is basically force times velocity, but then we have two phases. So it will be 2 times whatever is the force on one of the phase times whatever is the velocity that I'm pulling it with. Let's say the velocity is u infinity. And we already know what is F. F is basically the net frictional force acting on the surface, which we know from the local skin friction coefficient. So that is CFL times half rho infinity square. And we know for this is again a flat plate laminar boundary layer, assuming that it is laminar, which again is something that is not specified in the problem. We're assuming that this particular boundary layer that is developing here is laminar. In that particular case, we know the value of CFL. CFL is basically 1.328 by square root of REL, which is so this is my PC. So the mechanical power required to pull the plate at when the ambient and plate are at the same temperature is something like this. 1.38 times rho infinity cube square root of mu by u infinity n. So what we are trying to do is we want to reduce this power consumption somehow. So for that what we are doing is, okay, let's heat the plate. So if you heat the plate, what will happen is near to the plate the temperature will increase, like a boundary layer will form, thermal boundary layer will start forming. When a thermal boundary layer forms, here the temperature will be higher. So this is water. For water, if temperature increases, what will happen to viscosity? So as the temperature keeps increasing, the viscosity will keep decreasing. So if the viscosity reduces, then what will happen is, as your viscosity gets reduced, then your the net power consumption will also get reduced. So that is the whole idea behind this. So what we are trying to do is, in order to reduce the power to pull this particular plate, we are trying to heat the surface of the plate. So the plate is heated, then the thermal boundary layer will develop that will increase the local temperature, which will reduce the viscosity, and that should reduce my power consumption. That is the whole idea here. So the question now is, what is the ratio of these powers? So under the cool plate and versus the hot plate, how much power reduction will actually happen? So assuming all other properties are constant, so this is straightforward. So pH by Pc is basically square root of mu h by mu c. All I need to know are these values, mu h and mu c, that you can compute from this relation. So the correlation between temperature and kinematic viscosity. So if you substitute T equals to, okay, that is another question that I would like you to answer. So what temperature should I substitute? At 10 degrees Celsius, mu equal to 10 degrees Celsius is basically T equals to 283 Kelvin. So my nu will be so I'm getting this value around 1.298 millimeters square per second. So what about mu h? At what temperature should I compute the mu h value? All these boundary layer equations, or most of these cases that you will be seeing in upcoming weeks also, there is something called the film temperature. That is where all the properties have to be calculated at. So the film temperature here is when the plate is at 90 Celsius. First, we identify what is called film temperature, which is basically the mean temperature of the wall and the fluid, which is 90 plus 10 by 2, which will give me around 323 Kelvin. So if the film temperature is 323 Kelvin, you calculate the nu at this particular temperature at 323 Kelvin. So if you substitute 323, I'm getting around 0.55 millimeters square per second. So now that I have the values of mu h and mu c, I can directly compute pH by Pc. So I'm getting this around 0.65. So what you can see is, say, just by heating the plate by around 80 degrees Celsius. So if I heat the plate by 80 degrees Celsius, the pH has reduced by, from pH by Pc has reduced this one. So this is how much reduction? Pc minus pH by Pc is 0.35. This implies 35% reduction. So I can reduce the power consumption to pull the plate by heating the plate. So obviously the question now is this worth doing? How do I know whether it is worth doing or not? That is again straightforward, right? So the only competition here is between the savings that I'm getting by this, and indirectly I'm supplying energy somewhere. So indirectly I'm supplying energy so that I can maintain this temperature at 90 degrees Celsius. So what happens when a thermal boundary layer forms? There will be continuous energy dissipation from the plate because of because the plate is at higher temperature than the ambient. So if so in order to maintain the temperature at 90 degrees Celsius, what I have to do is I have to continuously give energy to it. And how much energy I have to give is basically to balance out what is the amount of energy, net energy that is lost into the ambient. So if I know the Nusselt number, which I already know from the correlation that I have before, I'll calculate the Nusselt number. From that, I'll calculate what is the net heat flux, net heat that is leaving from the plate. And that net heat is something that I have to continuously supply. So that is the energy that I have to supply. Say if you are using an electrical resistor heater, or depending on what type of heater, multiply that with efficiency, and then that is the energy you are spending in order to maintain it 90 degrees Celsius. And this is the savings you are getting by increasing the temperature. So if that particular energy is less than this reduction that you are going to get, so if for example that particular energy that you are going to spend there, when in case of PC, the energy is zero, like when both the temperatures are equal to each other, then you don't have to spend energy. But if let's say this is 90 degrees Celsius, then you have to spend some energy, you have to give some energy, the net heat flux that is lost. So the ratio of that energy with respect to PC minus pH, if that particular quantity is greater than 1, then this is advantageous. If the net heat flux is way higher than the particular value of pH minus PC, that PC minus pH that you are getting, then you have to exclude that particular this idea. So that depends again on the Prandtl number of the fluid, because the Nusselt number will depend on the Prandtl number and the velocity with which you are tracking, the length of the plate. So basically it depends on the Reynolds number and Prandtl number. That will decide what is the net heat that you have to actually supply compared with this particular reduction in power that you are going to get. Is that clear? Yeah, I guess there are no questions. Okay, then we move on to the next problem. This is again a standard case. So the wind blows at 0.5 meter per second parallel to the short side of the flat roof with a rectangular area. The roof temperature is given and temperature of air free stream is given. Calculate the total force and the net heat transfer, assuming it to be laminar force convection. So you have a roof. So this is 20 meter, this is 10 meter. And we are saying that the air is flowing parallel to it, so air flows like this with a velocity 0.5 meter per second and temperature of 20 degrees Celsius. This roof is at 40 degrees Celsius because the solar radiation is falling on the top of the roof, and because of which the roof temperature is increased. Question now is, what is the total force experienced on this and the net heat transfer rate? What are the terms that I would be requiring now? The first thing is I need to calculate the force. Let's say we'll start with the force. What is the equation for the force? We have just written it down here. It's basically CFL times half rho u infinity square, which will give me 0.664 times rho infinity square. Again, this is for force per unit width of the plate. Like if you just show the derivation again. The way we defined it is this particular quantity is force per unit width. So you have to multiply with the width to calculate the net force. Okay. So I substitute the value. So I have Q infinity as 0.5 meter per second. L is along the plate length, so that is 10 meter. W is perpendicular to it, which is 20 meter. Now the properties. All the properties have to be calculated at the film temperature, which is the mean temperature of the wall and the roof. So at 30 degrees Celsius, what is the value of mu per air? You can just quickly get it. So I have the new value, I have all these values, so I can substitute them back. You also get the density value. Did I miss something here? Okay, CFL times this will be force per unit area, so I have to multiply this with L so that I'll get the net force. So this is basically pressure times area is N times W. You can compute RL. I have the net force. Now similarly, what is the net heat transfer rate? So to calculate net heat transfer rate, I would be needing the Nusselt number. The net heat transfer rate from the wall is the average Nusselt number times the heat transfer purely because of convection, which is K times TW minus T infinity by L. This is the heat transfer per unit area multiplied with the area. And Nusselt number, the mean Nusselt number is given by 0.664 REL to the power half, Prandtl to the power 1 by 3, K times TW minus T infinite times W. So you can substitute all the values. You can take K to be 0.026, and you can take Prandtl number to be 0.71. That should give you the value of Q. You can tell me whether you are getting the same answer or not. I hope this is clear. Are there any questions? Yeah, I guess there are no questions. So then we'll move on to the next problem. So here is a different scenario. So till now we are interested in focusing on, okay, given the velocity and temperature, find the net heat flux or something like that. But let's say we are interested in the inverse problem, where you will be given the heat flux in an indirect way. So basically what we are trying to do now is come up with a way to measure the free stream velocity u infinity. So there is some flow that is happening. So we insert a thin metallic strip inside the flow such that if the strip is like this, it is very thin and the flow is happening on the surface of the strip. So this width is very high so that still the laminar 2D assumption is valid. And what we are doing is we are heating this strip with a known heat flux. We know that the power dissipation is 0.03 watt per centimeter square. Because how do we know that the power dissipation is constant? You say you put a resistance heating or something, and you know how much power you are supplying from this, and you measure the temperature on the surface of this particular thin strip. And if the temperature is not changing and the strip is in steady state, and if it is in steady state, the net heat that is given should be equal to the net heat that is dissipated. So the net heat that is given is something that you can measure, which will be equal to the net heat that is dissipated. So that heat is given to you as 0.03 watt per square centimeter. So I'll put it in other words, we know that the net heat flux from the surface is, if you convert it into meter square, so that will be 300 watt per square meter. I know the length to be 2 centimeter. I'll just put everything in meters. The question now is, if I also know the temperature, so if I know TW to be 30 and T infinity to be 20, how do I estimate U infinity? Because I know QW prime and I use the boundary layer. I know that laminar boundary layer assumption is valid here. So in that particular case, what we can do is we know QW prime to be equal to the mean Nusselt number times Kf by L, and you can take Kf to be 0.026. And the mean Nusselt number is given by 0.664 times Reynolds number U infinity L by nu power half and Prandtl number to the power 1 by 3. So we know all the values, you can substitute the values here. So take Prandtl number to be 0.71 and you can take mu to be 1.6 into 10 power minus 6. So this will give you so this is just another way to use this boundary layer theory where you can actually come up with a device that will actually measure it. But again, there are some assumptions that we are taking here. One is this particular correlation that we derived, that Nusselt number is 0.664 into Reynolds to the power half and Prandtl to the power 1. This is derived under a special case where we assume that the wall has to be uniform and constant temperature. So that is true only when you use a metallic strip with a very high thermal conductivity. So if the metal strip has a very high thermal conductivity, then the temperature variations along the plate will be negligible. So that is one that you have to ensure. And second, we have to assume that the plate is very thin so that it doesn't obstruct the flow. And another assumption that we have taken is the flow is laminar over this plate, so and it has to be aligned with the direction of U infinity. Like the plate has to be placed in such a way that it is parallel to U infinity. The question now is in reality, say when you are doing an experiment where you do not know what the actual velocity is, how do you know at what angle do you have to place the plate? Like now it is, if the plate is parallel to the velocity, we can compute the velocity directly. But most often the case is you do not know what the direction of velocity is beforehand itself. So then you have to keep the plate in different angles, and then like you can't keep rotating the plate at different angles and say, so you'll keep the plate at 2 or 3 different angles, and from then you'll try to infer what the actual velocity is. So this is a principle that will be used in hot wire anemometry. Whoever is interested in that particular technique can actually go and read about it on internet. Now you have GPT, which can give you all the necessary details how this technique can actually be used to find the velocity, not just one, like all the 3 components of the velocity, and different electrical setups that are required to heat this and stuff. Everything will be there in the internet, so you can go through if you're interested. But the principle is this: the idea is we assume that the velocity, the flow is still in the laminar regime, so for which we already derived what the heat flux could actually be, from which we'll estimate the Reynolds number. Once we know the Reynolds number estimate, from there we can calculate the velocity. Are there any questions in this? These are the applications of what you have learned in the lecture. Okay. The last one is again an extension of the problem that we have solved last week, where you have something called a fin, is an extended surface, where there is, okay, now we will remove the heat generation term. Assume the flow is one-dimensional, I mean the temperature is one-dimensional, and this temperature is Tb. The wall temperature is Tb. The wall temperature is Tb, and then the flow is happening from top like this. So this will be longer one. So this will be the length along which the boundary layer will be developing. So the flow will be developing like this. We're assuming that flow to be laminar, 2D, like all the Blasius assumptions that we have considered before. So under that particular case, you can write hp by k, that this is basically my Nusselt number, mean Nusselt number along the length direction along which the flow is happening, which is b. So hp by kf as 0.664 times Prandtl to the power 1 by 3, and the Reynolds number along that particular length direction times half. And from the Finn equation, this is something that you will come across in your heat transfer course, where the Finn equation is given by square root of h back times delta T times tan h ml, where m is given by this particular expression. H is a heat transfer coefficient, from which you can get P is the perimeter of this, and K is the thermal conductivity of the solid material. A is basically the cross section area of this particular area. So assume that the thickness is specified to you. So this thickness is specified to you, and the volume is constant. The total volume is constant. All we are trying to do is I'm trying to design a fin in such a way that all I need to decide is what should be the length and what should be the this b value. So I have to decide the geometry of the fin in such a way that will maximize the heat transfer from the surface. So this is some hot surface from which there is a fin that is extending, and I'm trying to find what is optimal value of B that will maximize my heat transfer. So if I increase B, then the corresponding length will be reduced because the total volume and thickness are constant. So the equations will be something like, if I write my volume as LBT, and I'm saying this is constant and T is constant, so if B increases, then L will decrease. So you have to, what we are trying to do is we are continuously trying to vary B in such and see whether I'll have any optimal value of Q. So the first question is, whenever we are saying anything optimal, there is some trade-off. So what happens if you increase B? If I increase B, then the boundary layer will keep on increasing. So as you keep on increasing, the amount of heat transfer will keep increasing. But what will happen is this length will decrease. So the total area available for heat transfer will also reduce. like if this thickness, okay, maybe the image is not showing correctly, so it should be something like length should be very much higher than t, depth should be very much higher than t. Maybe I should have drawn t to be lower than b. It appears here that t is larger, but t is very small, so t is the least dimension of all. So this is very small, so this and this are very close to each other compared to this and this. So in that particular case, the heat transfer from the top and bottom surfaces are neglected. But if the length is large, then the temperature here will actually reach T infinity, and that we have seen even in the last case, in the last week problem, where as the x tends to infinite, then in the governing equation that you see where there is a heat generation term, but here there is no heat generation term. So this Tb will initially be close to the wall temperature, and as you go far and far, it will keep on reducing it to T naught, right? Okay. So what will happen if B, like if B keeps on increasing, then beyond a particular point, the heat transfer will be reduced because this length will be very short. So this will be very close. When this is very close, the temperature here will be very high. But if B is very small, then length will be very large. Then the temperature difference, like it cannot be too small or it cannot be too large. We'll quantify these things once we derive the equations. So let's say it's just a little bit of manipulation here, like mathematical, like you just interchange the terms. So as usual, we'll start with, we'll try to get the equation in terms of some non-dimensional terms. So let's say in this equation, T is again a constant. So let's say I divide this equation with T cube. So this will be L by T times B by T times 1. So if I see my heat transfer coefficient, H is given by, this is anyways a constant. So I'll write this as REB to the power half times Kf by B. Now let's say I can write, I'll define new Reynolds number RET as U infinity T by nu. I can just take this as B by nu times T by B. So this implies, if I take this on the other side, so B by T times RET will be my REP. So this equation I can use back here, which will give me Kf by B times Prandtl to the power 1 by 3 B by 2 to the power half. So let's compute each of these terms individually. Let's say first I'll compute the m value, which is square root of hb by ka. I have my h equation already, so that will be 0.664, or let's just calculate m square. Then I can take the square root. This will give me 0.664 times kf by k. Again, this is another non-dimensional group that I can take, times Prandtl to the power 1 by 3. RET is again a non-dimensional number. B by T is a non-dimensional number. I have a 1 by B, and then I have P by A. P is basically 2 times B plus T, and area is B times T, right? So if I group the terms together, so I have 0.664 into 2, 1.328. The first term is Kf by K, and then I have Prandtl to the power 1 by 3, RET to the power half. And as we see, B is very much greater than T, so I can assume this to be closely equal to B. So that will leave me with 1 by B by T times T square times B by T to the power half. So from this, I can write my expression for m into L, which is square root of this entire term into L. So if I take a square root, t square will come out, so that will be t, so that will become L by t, square root of 1.328. This will be kf by k to the power half, parental to the power 1 by 6, ret to the power 1 by 4, and then I have a b by t to the power minus half, so that will be b by t to the power minus 1 by 4. So this is my m into L. Just to write it in simple way, our parameter is this b by t. So I know v is basically L by t into b by t, so I can substitute that back here. So that will give me b by t cube into, I'll call this entire term as some constant b into, so L by t is basically v by b by t, so b by t, so this will become b by t to the power minus 5 by 4, where my b is basically, I'll just take it in the next page. Since L by t is basically v by t cube divided by b by t, if I substitute and write it as b times b by t to the power minus 5 by 4, where b is this big term, whatever we have, b by t cube times square root of 1.328 kf by k to the power half, granted to the power 1 by 6, and then a new Reynolds number to the power 1 by 4. So this is something that we have in the root over hp by k. So this is basically my m into L. Now there is another term here, that is the root over hp k. If you take that term, so hp k is h we already have, p is also something that we already have, 2 times b plus t, area is b times t, and then I have my k value here. So just like before, if you take the, we have kf by k, so I'll take k outside. So this will leave me with the, okay, I have to multiply and divide with k so that I can get k outside, and this b and b will just cancel out. And here b plus t is, I can approximate this as b because the b is very much greater than t. With those assumptions, this will be k square times 0.664. So I have you can write it as 1.38 kf by k until to the power 1 by 3 ret to the power half, and then here I have a b by t to the power half into, I'll again multiply and divide with t, so I'll get something like this. So this will leave me with 1.328 k square kf by k to the power 1 by 3 I to the power half b by t to the power 3 by 2, and then I have t square here, right? Now I can calculate square root of h back, which is again something similar to what we have before. That will be square root of 1.328 kt will come outside. This will be kf by k to the power half p to the power 1 by 6 ret to the power half, and then I have a b by t to the power 3 by 4. So again I can call this entire term together. So this entire term together is what we have before. It's k times t times b by t cube into b by t to the power 3 by 4, right? Now I'll calculate my q. Q is Tb minus T naught times root over h bar, which is Kt b by tq into b by t to the power 3 by 4 into tan h ml. ml is basically b into b by 2 to the power minus 5 by 4. So this is my q. So this entire thing is a function of just b by t. So all we need to find is the corresponding b which will maximize the value of q. So this is something very similar to what we have done in the last week. So we try to maximize this function. So what we have to do is, yeah, let's say like we take everything as constant. So we say some constant a equal to tb minus t naught into k. Everything, all these parameters are known and given to us. So I can call them as a, and let's say x equal to b into d by t and something somewhere. Yeah. So I'll call this term as something like this. Or let's just say a as this and say we define a new variable y as b by t or x as b by t. So then we can find the corresponding optimal value of x. So which will reduce my q as a function of x, sum a times b times x to the power 3 by 4 times tan h to the power bx to the power minus 5 by 4. And what we are trying to find is x star such that q of x is maximum. And how do we do that? Again, this is very similar to what we did last week as well. So all you have to do is dq dx equal to 0 and then solve for x star. So what is dq dx? ab into, just use the chain rule. So it will be 3 by 4 x to the power minus 1 by 4 into tan h of bx to the power minus 5 by 4 plus x to the power 3 by 4. Derivative of tan hx is secant h square x of whatever is here, and then b times minus 5 by 4 minus 9 by 4 equals 0. So that should give me 3 by 5 x to the power minus 1 by 4 tan h of b x to the power minus 5 by 4 equals to secant h square b x to the power minus 5 by 4. This is x to the power minus 3 minus 9, 6 by 4 into b. So this is the secant h square is 1 by cos h square x. So if I just rearrange the terms, it will be 3 by 5 into, I'll take x that side and secant h square this side. Tan hx into secant h square x is sin h of bx to the power minus 5 by 4 into cos h of bx to the power minus 5 by 4 that should be equal to b into minus 6 plus 1 minus 5 by 4. So let's take say y equals to px to the power minus 5 by 4. This implies if I just multiply divide with 2, it will be 3 by 10 into sine h of 2y equals to y. So this is the equation that we'll be solving. This again you can use any technique that you know, so Newton-Raphson or any other method that you know to solve nonlinear equations. So use any of that technique and then you can find the solution for this. So I'm getting a value of around 0.911. So if y equal to this, then all we have to do is b into x to the power minus 5 by 4 is 0.911, which will give me x to the power straight that directly. This implies 0.911 to the power minus 4 by 5 to b to the power 4 by 5. Right? So this is around 1.0708 b to the power 4 by 5. And x is my optimal b by t value. So b optimal by t is 1.08 times b to the power 4 by 5, and b is something that we have already defined as this. Just rearrange. (1.21) into power 4 by 5. This is the final expression that we are getting in terms of non-dimensional equation, in terms of the ratio of conductivities, Prandtl, Reynolds number, and the non-dimensional volume. So if you forget about the equation, the term that you see for q of x is something like this: x to the power 3 by 4 and tan h of bx to the power minus 1 5 by 4. So tan hx is something between minus 1 and 1. So if the x value keeps on increasing, then tan h will go close to 1. So, but if x value increases here, then this particular term will decrease. So tan h will become close to 0. But if x is increasing, this particular term is increasing. So if you try to plot something like this, so it should be something like something like this. So if x is very low, then one of the term is dominating. So if x is very low, tan h term might be dominating initially. So it will keep on increasing, but beyond a point, as x increases, this particular value will tend to 0, and then this function will keep starting increasing. So there will be some optimal point where both of them has to match each other, and that's where this particular solution is. That is this optimal value at which the q will be maximum. Okay. Are there any questions in this? I have not taken any problems related with how to apply the similarity method. Maybe in the next week, once the integral solution comes, we'll see other ways to solve the same problem that we have solved in this week. Like, we haven't actually solved the problem, we have directly presented you the solution. But in the next week, we'll actually solve the problem in a different way and obtain what is the value of the screen friction coefficient and all, the Nusselt number, and etc. in a different way. Okay, if there are no further questions, then I think we can conclude the session for this week. Okay, thank you all for joining. We'll meet next week, same time, 5 to 7 next Saturday.